All right, hello and welcome back. Today we're going to do another worked example of sketching a curve. In the last video, I went over how to sketch the curve and what all of the steps are. So if you missed that one and want to know what are the steps exactly, and also to see another worked example, go watch the last one. I'll have it linked in the description as well, the previous video. Okay, but for today, I'm going to go through this worked example because the last example didn't really encompass all situations. In the last example, there were no asymptotes, for example, and in this example, there will be asymptotes, and so I feel like it's important to do multiple different ones, right? So let's go ahead and do the same steps we did in the previous video, but on this function, which is quite different from the last function. Good. All right, so Number one is to find out what are the intercepts. Well, to find the y-intercept, we must set x at 0. So let's find f of 0. That's going to be 4 over 0 minus 1, which is negative 4. Awesome. So our y-intercept, that was easy, is going to be negative 4. There we go. Now, what about x-intercepts? We would have to set y to 0, so we'd have to do 0 equals 4 over x squared minus 1, which then we would get something false. We would get 0 equals to 4 when we cross multiplied up. So therefore, there is no x-intercept. And that is okay, by the way. We do not have to always have an x-intercept, but what this does mean is that in this example, we actually will not ever cross the x-axis. Now, how is it possible, you say, that we wouldn't cross the x-axis? Well, there's many possibilities. If this were a quadratic, which it isn't, it's sometimes possible that we have our vertex above our x-axis line and we open up, or that we have it below our x-axis line and open down. So that's a possibility. Also, we might have asymptotes at play here, which might contribute to that. And so let's see if that's the case here. I believe it is, and we'll move on to that in the next step. But don't panic if it doesn't seem like there is any x-intercept, because not all functions have to have an x-intercept. And in this case, we have none. Okay, so number 2 is what are the vertical asymptotes? VA. So what's our criteria for vertical asymptote? It's where is the denominator going to be 0? So if we were to factor this denominator, we'd get 4 over x minus 1, x plus 1, like that, which would mean that we'd have vertical asymptotes at x equals 1 and x equals to minus 1 and no others. Now, how do we know these are both definitely vertical asymptotes and they're not holes? Well, we know this because we cannot cancel out these, we can't cancel these things out with anything on the top. The top is just 4, and 4 does not factor into or simplify into x minus 1 or x plus 1, and so therefore we can't do it, right? We can't do that. Number 3 asks about horizontal asymptotes. Let's just remind ourselves what's the criteria for horizontal asymptotes. Basically, if the degree of the numerator is higher, then that means that there is no horizontal asymptote. And if the degree of the denominator is higher, then the horizontal asymptote is 0, which I'll just write that down now because that is the case here. The degree of the numerator is 0, and the degree of the denominator is 2. So therefore, we would have a horizontal asymptote. Now, the other option is if the degree of the numerator and denominator were the same, then it would just be those coefficients of the that are associated with that value. The coefficients of the highest degree terms of numerator and denominator. Now, what about oblique asymptotes? Well, if we have a horizontal asymptote, we definitely cannot have an oblique one, so there's none. But even going back to the criteria, it says that the degree of the numerator must be exactly 1 degree higher than that of the denominator, and that's not the case, right? As we said before, it's actually the denominator degree that is higher, so not only is it not exactly 1 degree higher on the numerator, it's just not higher whatsoever for the numerator, so it's not going to work. So that's exactly why too. if we have a horizontal asymptote, we can't have an oblique asymptote as well. It's possible we don't have either of them, but if we have horizontal, we can't have oblique, and if we have oblique, we can't have horizontal. Okay, very good. Let's move on to step 5, which is the first derivative test. And as a reminder, this test tests for what are the critical values, right? What are minimums and maximums of the original function, right? Because that's going to show us the turning points, which is minimum and maximum. Okay, so let's do that. Let's go ahead and do that. So what is the first derivative? Well, the first derivative, according to the quotient rule, says we need to take derivative of the top times the bottom, which derivative of the top is just 0. So that's going to turn into nothing, minus the derivative of the bottom, which is 2x, times the top, which is 4. And that's all over the denominator squared, although that won't matter in a second because we're about to set this to 0 anyway, but I'm still going to write it down for the sake of completing that quotient rule as we always do. And then I'm going to simplify this one, and I'm also going to set f prime of x to 0, right? Because that's going to tell us where those critical points are when we do that. So 0 is equal to negative 8x over 2x squared, x squared minus 1 squared. That means negative 8x is equal to 0. That means x is 0. So therefore, we have one critical value at x equals to 0. Now, what's the other value when x equals 0? We actually already found with our intercept that it's negative 4. So therefore, 0 comma negative 4 is the minimum or maximum. Now, we don't know which one it is just yet. We'll find that out in the next step, but we know that it's the minimum or maximum. And then once we've learned, I'm going to circle which one it is. Okay? But yeah, there we go. So, and I also want to point out too that I know in this situation our intercept turned out to be a critical point, and that is possible, but it's not always the case. Oftentimes, the critical values and the intercepts are not going to be the same points. In the last work example, they certainly were not, I don't think. So, just keep that in mind, that just because that happened today and it was just a coincidence, it doesn't mean that it's likely to be or that it always will be, just because it happened in one situation here. Okay, good, very good. Let's move on to number 6, which is where we are going to find out where we have increasing intervals and decreasing intervals. So let's say we have above 0 and below 0. So the interval from negative infinity to 0 and the interval from 0 to infinity. So let's plug in a number to our derivative to find out if it's positive or negative. Because remember, if it's positive, that means we have an increasing interval on the original function. And if it's negative, we have a decreasing interval on our original function. So let's say I plug in minus 1 back in. What am I going to get? Let's see, minus 1 to this original function here, the original first derivative. If I plug in negative 1, I will get something positive, right? Because I will get something positive on the bottom always because I'm squaring something. And then over here, I will get, if I put in something positive, I will get something negative. So this goes for all those points on the interval, except for the asymptote. So I should mention that it excludes asymptotes. So the increasing intervals would be what? It would be negative infinity up to negative 1 and negative 1 to 0. Now, why did I do that, even though I wrote the full intervals here? Well, it's because in my final answer, I would like to exclude the asymptotes, and keep in mind that these values are going to be undefined at the asymptote, right? Because there is no slope with a tangent right at the asymptote, so that's why. I could even write this here as well, that it would have to be between, you know what, I probably should write it here as well, that that's the case. But it's most important that you make sure you write that in the final answer. If there are asymptotes, remember that we must skip over them. It is mandatory. And then the decreasing intervals are where the second derivative was a negative value. So 0, 1, and 1 to infinity. All right, very good. Awesome. Okay, let's move on to step number 7. We're going to need another page for that, but that's no problem. Let's grab another page quickly. Let's find f double prime of x, right? Or that's just what I like to call it. It's really called the second derivative. But to find the second derivative, we need to grab the first derivative first off, which was negative 8x over x squared minus 1 squared. Negative 8x, x squared minus 1 squared is our original first derivative. So our second derivative would be the derivative of that. So let's figure it out. So derivative of the top would be negative 8 times the bottom, x squared minus 1 squared, minus derivative of the bottom, which is 2x squared minus 1 times 2x, and then times the top, like that. And then f double prime of x is equal to negative 8 x to the power of 4 minus, let's see, double the product, minus 2x squared plus 1 minus, let's see, let's multiply these three together. So 2 times 2 is 4. 4 times negative 8 is 32. Okay, cool. So we're multiplying negative 2 times this. Yeah, this is going to be plus 32x squared, and then times x squared minus 1. So I multiplied these three numbers together. I just want to be clear what I did there, and that's what I did. And then that's all over x squared minus 1 to the power 4. Not that it matters, but I'm just going to write it anyway because that is what it is. Awesome. And then let's simplify further. Negative 8x to the 4 plus 16x squared minus 8 plus 32x to the 4 minus 32x squared. Like that. And then I'm going to set this to 0. We can set it to 0 at any point, really. There's not really a common place you have to or something. And I'm also going to simplify this one step further and say we have 32 minus 8 as our coefficients for x to the power 4. So that's going to give us 24 x to the power of 4. As you can tell, mental math is my strong suit. And then we have 16x squared minus 32x squared, which is negative 16x squared, and we add those up. And then minus 8, and that's all over x squared minus 1 to the power 4. Now that's just going to disappear when we cross multiply it up to 0, right? It's all going to disappear. So we're then going to have 0 is equal to all this stuff, all the stuff on the top. Now, I'm going to actually factor out an 8 because I can, and it will make my life easier if I choose to do that. So 8 times 3 is 24. 8 times 2, 8 times minus 1. There we go. Now, I recognize this is not a quadratic. However, it has the proportions of a quadratic, so I can somewhat treat it like a quadratic if I am going to factor it. So I'm going to use the same factoring method to factor this that I would use to factor a quadratic. So let's use decomposition. Minus 3 over here and minus 2 over here. And again, we want two things that multiply to negative 3 and add up to negative 2. All right, so negative 3. Well, let's see, it's minus 1 times 3 and 1 times minus 3. So what's that? And then for 2, negative 1 times 2 and 1 times negative 2. Okay. So let's think about this. We would like, oh, I've done this a little bit incorrectly, or have I? No, we didn't need this part. My apologies. So we just want to know which one of these things, if we added them up, would give us negative 2. And of course, it'd be this one. 1 minus 3 is negative 2. So that's what we're going to do. Perfect. So 8 times, which we can actually just get rid of if we wanted, doesn't actually make a difference though. 3x to the power of 4 minus 3x squared plus x squared, right? Here's our negative 3 and here's our invisible 1, minus 1. And then I'm going to factor. I'm going to say 0 is equal to 8, 3x squared times x squared minus 1 plus 1 times x squared minus 1. So that means 0 is equal to 8, 3x squared plus 1, x squared plus 1. And the 3x squared plus 1, now that's a sum, right? That's a sum, so we cannot factor that further. That is okay as it is. Yeah, that's not really something we can do much about. But then on the x squared, it should be minus 1. I was going to say the x squared minus 1, we can factor that, right? To this, x plus 1, x minus 1, like that. Awesome. So how can we use the zero product property to get to 0? Well, for 8 is never going to be 0, so we can just skip that one. 3x squared plus 1, this is also never going to be 0, but here's why. Let's say we plug in 0 as x, we would still get 1. Let's say we plug in any other value, we'll get something greater than 1. Because this 3x squared the lowest it can be is 0. That's its minimum. And then we're adding 1 to 0, or we're adding 1 to some other positive number. We're always going to get something positive. We're never going to get 0. Never, ever. And then over here, we could get 0 if x is equal to 1, and if x is equal to minus 1. So therefore, x is equal to 1 and x is equal to minus 1, which happen to be the asymptotes, is where we switch our concavity. Right? So our concavity switches only where the asymptotes are, and that's very, very key. That's very important, okay? So I still am going to do the next step, but it's not going to be the same as normal, right? Normally I'd plug in x equals 1 to the original equation to get the y values here for the switches in concavity, but there's actually no points of inflection. These are just concavity switches because of the asymptotes, because these are exactly where the asymptotes are. Okay, so let's still go to the next step and see what we can see. Negative 1 and 1. Okay, so on this interval here, from negative infinity up to negative 1, we would have concave up, right? F negative is going to be plus, so we have concave up, right? Concave up, negative infinity to negative 1. Then over here, from negative 1 to 1, we have concave down. And why is that? We have concave down because if we plug in something here, right, like 0, we're going to get f double prime is negative, right? It's minus for the second derivative. And what about the second derivative of the interval from 1 to infinity? Well, that's going to be concave up once again. So that looks like this function is mostly concave up. It doesn't seem to be concave down all that often at all, only from negative 1 to 1. So, yeah. Well, there we have it. We did it. Now all we need to do is sketch the curve. So let's sketch the curve. Okay. Very good. Let's draw some nice straight lines. And I'm going to go back and refer to our previous work in order to get this. But before I do that, I'm going to go ahead and just label my graph. Let's see, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. Very good. Awesome. Okay, cool. So let's move on to what are the intercepts. Well, there's no x-intercept, and the y-intercept is 0, negative 4. So I'm going to write that in, that it's 0, negative 4. And let's see, how many negative values do we have coming up? Not that many, so actually I'm going to use the same scale as I used earlier. Oh, and now I need to draw this again. Oops. There we go. Let's not make our line so short. There we go. So 0, -4. There we go. Next, I'm going to label my asymptotes. So I have asymptotes at x equals -1. So those I'm just going to draw as dotted lines on my graph. So, or dashed lines, I guess I should say. And then we also have a one at where? We also have one at y equals 0, and there's no oblique asymptotes. So this one's harder kind of to see the dashes. For this one, I'm going to make it clear this is an asymptote at y equals 0, just because it's kind of hard to see that with the regular axis line as well. With the other ones, it's pretty clear since we're drawing, dashed lines that it's asymptotes. We could also directly state that too if we wanted, but maybe not as crucial as for the other one. Okay, and then next we need to see where we are increasing or decreasing. So we're only decreasing between the asymptotes. We're only decreasing here. And we're increasing everywhere else. We're increasing. Or are we? Sorry, one second. I think I read this a little bit wrong. No, so I did read this wrong. So we're increasing all the way up to 0. So we're increasing from -infinity to -1, right? Which makes sense. This is increasing. We're also increasing from -1 up to 0. So we're increasing. Then we're decreasing from 0 to 1. And then we're also decreasing over here, right? Also decreasing here again. Now I'm going to check to make sure my concave up and concave down is what we expected. So the change in concavity, according to my algebra, says that we should be concave down between the asymptotes. That's what I was getting at, but between the asymptotes. I think I referred to the wrong thing there. But anyway, our concavity should be concave down there and concave up before and after those asymptotes. And they are. That is the case. And so that looks good. So this is a good sketch of the graph because we drew the intercepts like we were supposed to. We made sure we complied with the rules about increasing and decreasing intervals, with the concavity rules. We also drew in all of our asymptotes. So those are the main things. The main 4 things on our checklist are intercepts are correct, and asymptotes are correct, and then increasing, decreasing intervals are correct, along with like the minimums, maximums, things like that. But this one's clearly labeled here as the maximum. And then the last but not least, the concavity and points of inflection, which in this case we did have a change in concavity, but the changes in concavity were due to the asymptotes, not due to any points of inflection. There were no points of inflection in this situation. So there we have it. We did it, and that's quite good. Yeah, and also too, given that there was an asymptote at y equals 0, now it makes sense why there was no intercept. Because if we're not allowed to touch that line y equals 0, then how could there be an x-intercept? It'll never happen. We'll get infinitely close to having one on both sides, actually, in 2 ways, but we'll never quite have one. And so that's why we have that asymptote there. All right, well, that is everything for today. I hope you enjoyed this second worked example, and we hope to see you in the next unit. There will also be a third worked example as well at some point, too. Okay, so we'll see you for that. We'll also see you for Unit 5. Bye, everyone.